always get an elliptical galaxy. The difficulty in simulations is still to produce spiral galaxies. So people are working on that, but there are quite a few unsolved questions. A very general picture here is that if you have gas clouds with little or no rotation that start to collapse, very, very massive gas clouds, and start to form stars, would end up probably with a spheroidal distribution of gas and stars, which ultimately might lead to elliptical, however, usually also mergers are involved. If you have a rotating gas cloud, because of this rotation and the centrifugal force, ultimately you end up with a flattened spheroid and an extended gas-rich disk. If you have strong rotation, you would end up again with an extended disk, not necessarily with a spheroid in the center, and also eventually spiral arms. There are a number of theories as how to spiral arms evolve. Often these theories involve some perturbation that must have happened intrinsically or extrinsically in such a galaxy. So this picture here only looks at internal influences. However, we also know that, of course, external influences are quite important, such as mergers with smaller units, as you saw in the previous cosmological simulations. If you have mergers of roughly equal mass galaxies, or generally very massive galaxies, in the end, even if these galaxies initially had spiral structure, you end up with something that looks like one single massive elliptical galaxy. So both effects play a role. If we go one step further here and compare the overall star formation histories of elliptical galaxies and spiral galaxies, what we find typically is that elliptical galaxies formed most of their stars early on, at early times. So we find mainly relatively old stars in the present-day universe in these kinds of objects. That is indicated over here. In spiral galaxies, we tend to find very gas-rich objects over extended periods of time. The gas can be used to convert or to be converted into stars. So we have continuous star formation across basically the entire lifetime of the universe, such as is happening still in our Milky Way. So rather different evolutionary histories in these two types of galaxies. Also, in elliptical galaxies, early on, the gas gets consumed very rapidly. You have little rotation. The stars are mainly on chaotic orbits or elliptical orbits with no preferred rotational direction. Overall, in spiral galaxies, the disks of these spiral galaxies have a preferred direction of rotation, and that is where we find most of the ongoing star formation.
这边讲到是星系怎么做出来的啊？那星系刚刚讲它是有几千亿个恒星绕在一起的东西。那椭圆星系呢，是这些星球啊，大家互相绕啊，互相绕成一个椭圆的形状。螺旋星系呢，它有一个盘状的结构，多半的星星都在盘状里面做一个像我们太阳系一样公转的这样子的运动。螺旋星系里面还有很多气体，恒星正在还在做。椭圆星系呢，已经没有气体了，这种材料，恒星已经做完了，很早就做完了。那这边的这个理论就是在解释这些星系怎么做出来的，这个还没有答案。不过有一种理论认为，当时那一大团要做星系的那一团云气啊，如果转得比较慢，它就会变成椭圆星系。那他当时在做恒星的时候，他作为这一团气体，他就已经开始做恒星了，因为局部的气体是缩下去做恒星，所以它的恒星形成啊，在很短的一段时间，这是时间轴啊，在很短的时间他就把恒星形成啊做完了，所以现在它的恒星已经是做完活着的，已经活了很久。没有新的恒星在诞生，是一个老人的社会。可是这种螺旋星系呢，相信是一个当时那团云就转得比较快啊，天下万物没有不转的。这个东西如果不转的话，大家万物已经把它拿到中间就全部毁掉了。它一定要靠转，靠离心力来维持它的这个运动。那这个东西如果当时转得很快的话呢，大家相信它就会变成一个扁平。扁平的形状呢，气体在那里面又交互作用，所以原来形成的恒星 就留在原地。后来这一批缩下去的到盘状里面，就形成了新的恒星，形成了螺旋的结构。就这种星系的恒星形成的活动，拉的时间很长，它一直持续不断的有生老病死、生老病死这样子的生生不息的这样子的一个社会。
So ultimately, this combination of internal processes as well as external processes, such as mergers and interactions, leads then to this huge variety of different morphological galaxy types that we actually observe. You see here a collection of a range of different galaxies observed in the nearby universe. Most of them are actually spiral galaxies, some of them are elliptical galaxies. And the galaxies, of course, contain mainly gas, stars, dust, and also something that is not directly observable for us, dark matter. We infer the presence of dark matter, for instance, from the kinematics, from the motions of the stars in galaxies. With respect to the stars, I would now like to go to even smaller scales. As you may have noticed, I went from large-scale structure formation to galaxy formation. I would now like to move on to star formation, stellar evolution, and finally stellar nucleosynthesis. Stellar nucleosynthesis is important to understand because through nucleosynthesis, through the subsequent fusion of nuclei in stars, heavier elements are created, including those elements out of which we as human beings are composed, of which our Earth is composed, of which planetary systems are composed. So let's look at star formation, and I'm showing you here two images of a nearby spiral galaxy. Actually, it's the spiral galaxy closest to our own Milky Way, the Andromeda galaxy. You see an optical image of Andromeda over here, nice big spiral galaxy. And if you look at this image in other wavelength ranges, you see mainly those stars that dominate the light in these wavelength ranges. Over here, for instance, we see an UV, an ultraviolet image of M31, where most of the light is contributed by massive young stars that formed fairly recently in the spiral arms of Andromeda. So you see these spiral arms outlined by the bluish light of these massive stars. We can also go to completely different wavelength ranges, namely wavelength ranges in which gas dominates. For instance, if we go to the radio regime, at radio wavelengths, very long wavelengths, we can observe the light from different molecules, molecular clouds in which star formation happens. And note how well these molecular clouds that are shown now here in CO, carbon monoxide, outline the structure that we also see in these massive, recently formed young stars. So there's good correspondence between recent star formation and the location of massive molecular clouds. The general picture of star formation is, in fact, that stars form of gas clouds, in particular molecular clouds, which then collapse under their own gravity.
好，这张图很有意思啊，这是我们附近的一个星系啊，仙女座的星系，我们的邻居了啊。那它的可见光呢，大家常看到这样的照片，就这两是它的两个卫星的星系，我们不管它。它这边就有这些螺旋结构，那这些光啊，这些闪闪不太清楚的光是什么？那就是几千亿个恒星构成的。你用望远镜仔细看，就看到一颗一颗的恒星。那如果没有看，就模模糊糊成一片。这是我们眼睛看到的。那利用多波段、不同波段去探测不同的天体或不同的过程。这张照片是好像我们戴了一个紫外线的那个眼镜，不是太阳眼镜，太阳眼镜是隔离紫外线。我们现在戴一个眼镜，只看到紫外线，这是一个紫外线的人造卫星拍的。我们就会发现，跟刚才长相不太一样，就好像只有一颗的那种一点点出来了，就走在这些螺旋结构上面，这些就是一颗一颗很亮的恒星，单颗的，它发出很强的光，很高温，所以它有紫外线。左边这张图呢，现在就更有意思了，它是一氧化碳分子，这分子在转啊等等的时候，它也会发出一些辐射。我们就用电波的望远镜调到那个波段，去 侦测的是一氧化碳的分子。我们就发现这些分子啊，叫分子云，因为我们现在的理论相信分子云是做恒星的地方，把这些分子云的结构画出来，发现它真的跟这些大质量的恒星刚刚诞生的恒星结构是一模一样的。所以恒星是在分子云结构里面诞生出来，这就是我们活生生的看到恒星诞生的情形。
Most of the star formation in the present-day universe happens in the disks of spiral galaxies. That is also where we have the highest gas concentrations, including molecular gas. And the present picture that we have for star formation is maybe molecular clouds are sites of star formation. And these molecular clouds can collapse to form stars if their internal gravity is larger than the pressure. Pressure being motion of individual particles in these clouds that basically exert a pressure that can act outwardly, and maybe sometimes also radiation pressure acting outwardly. We have basically an interplay between this pressure that tries to drive clouds apart and their own gravity that tries to make these clouds contract. The gravity is larger than the pressure that clouds can contract, can collapse to form stars. This can only happen when the temperatures overall are fairly low, otherwise this pressure and these random motions of the particles are actually too big for the cloud to contract. So we need relatively cool regions. We need these regions to cool down sufficiently to form stars. A gas cloud can form a single star. A gas cloud can also be inhomogeneous, have several centers of higher density, which then contract individually and form multiple stars. Ultimately, this will also depend on the mass of that gas cloud. Because of the rotation of the cloud, when it starts to contract and to collapse, something like an accretion disk forms these disk-like structures which then typically have centers, very high density centers to which the material, the matter is flowing, and in these centers we could have star formation. So that's the overall picture, and we can actually observe that also in the nearby universe. I just want to show you a few images here of observed star formation. Here we have a nearby star-forming region. It's the so-called Orion Nebula in the constellation Orion. It is so luminous and so nearby that you can see it with your bare eyes on the night sky. Perhaps you recognize this constellation of stars. Basically, we have here a very luminous red star called Betelgeuse, a very luminous blue star called Sirius, the star that I used earlier in the example of how long the light travel times are towards Earth. And over here, in this region, we have a slightly extended area, the so-called Orion Nebula, at a distance of 460 parsecs. If you multiply that by 3, you get the distance in light years of this object. 3.2 will give you the distance in light years. This is an image of the Orion Nebula, a pretty famous astronomical image. And now let's take a close-up of what is happening in Orion. Orion is being illuminated by massive stars that formed in this nebula fairly recently. And some of these massive stars form a structure that is called trapezium, because it looks like the geometric structure of a trapezium with 4 different corners. You can see here these 4 bright stars. Blow up of this region is shown over here. 4 very luminous stars, very massive stars. The radiation of these massive stars formed recently begins to blow away the surrounding molecular gas, clearing these regions for our observations, and in doing so, it actually uncovers the location of a number of currently forming protostars, which are still surrounded by their, so to speak, birth cocoons of dense molecular material that is falling onto them. So you can see also that some of these have these seemingly cometary tails pointing away from the nearest massive star. This star in particular is responsible for this evacuation of the gas in different directions, thereby revealing these less massive, currently forming protostars in their vicinity. So, to move on, the general picture that we have of star formation is that we have collapse of gas clouds, subsequently the formation of very, very dense regions which continue to cool down, which continue to that gradually also the material begins to heat up again. We reach higher temperatures, increasingly higher temperatures, eventually such high temperatures that fusion can occur. Hydrogen begins to fusion into heavier elements, creating ultimately helium. Very similar to what happened in the early universe, only that now this is confined to these extremely dense regions in protostars. Once hydrogen fusion starts in stars, we say that these stars are now located on the so-called main sequence. We no longer consider them as protostars, as currently forming stars. What happens subsequently depends on the mass of the stars. Stars that are low mass objects will take a very long time for their hydrogen fusion. They stay in this phase for most of their life, and this life can actually extend over tens of billions of years. High mass stars have very short lifetimes. They burn up their fuel very, very rapidly. They're very luminous. They have lifetimes of just a few million years. So there are huge differences in the lifetimes. And also the subsequent evolution that stars experience depends strongly on their mass and how high the temperatures are that they can reach in their interiors, in their core regions. Several of these evolutionary stages are indicated here for less massive stars, stars with the mass of the sun. Basically, we would reach the stage on the main sequence, burning hydrogen. Once all the hydrogen has been burned up, obviously our sun is not yet at that stage, these stars evolve into so-called giants. Helium burning finally will begin. The stars continue to evolve. At some point, after they can no longer maintain fusion, they eject their outer shells, their outer atmospheric layers, becoming a planetary nebula. And in the centers we find a collapsed star, so-called white dwarf, which is still luminous for a while, but slowly cools out because it no longer undergoes fusion in its central regions. And white dwarfs reach very high densities, they have very small radii. So that would be the typical evolution of a low mass star. If we have higher mass stars, these stars first enter the mid-sequence phase, burn up their nuclear fusion, their nuclear material through fusion much, much faster, and then evolve into much bigger giants, namely supergiants with much larger radii. Our sun will be tiny in comparison to such a supergiant. The ultimate evolution of such a supergiant is that it will generate heavier and heavier elements in its core and in the surrounding regions, until nuclear fusion also here can no longer be maintained. At that point, the cores of these stars collapse, and we have the formation of massive supernovae. Very luminous supernovae, stars explode, eject all of their outer material, including the heavier elements that they generated in the previous nuclear burning phases. And the ultimate result, again, depends on the original stellar mass. It can be a neutron star, or stars in the intermediate mass regime, let's say stars in the regime of 10 solar masses or more, or they can actually go to the stage of becoming black holes, in which no more light can escape from these objects. For these, we would need very massive stars to be converted in their final stages into black holes.
Okay, that's a lot. Can you go back to maybe to Orion and 这边讲到的就是恒星的形成。我们原来讲说星系的形成是很大，几千亿颗恒星构成的团体。然后我们现在 zoom in 到里面，其中一颗恒星的周围，它物理是一模一样，还是一团云气，靠着万有引力收缩。一收缩呢，气流就会变快，一变快就会变扁，然后就会变成一个扁平的形状。其中一个例子就是晚上看到的猎户座。猎户座这些星球啊，它的这个距离跟我们都不太一样。演化的阶段也不太一样，有成年的星球、老年快爆炸的星球。这边呢是刚刚诞生的星球，看到很多气体跟尘埃混在一起，就是星球正在诞生的地方。然后呢 ，the next one please。那这就是刚才的那个一个，我们平常叫它4核星，还有4颗星，有4个很亮的恒星。这些恒星呢发出很强的紫外线。把周围的气体都给激发起来，激发了以后云气就会发光，所以这一段是因为没有资料， 但是这整块区域啊都是发光的气体，发光的气体，这都是刚刚诞生的恒星跟周围气体的交互作用。他刚刚特别讲到说，这个气体发出来的光，发出来的风，吹出来的气体啊，会把周围的这些刚刚诞生的恒星啊，比较小质量的呢，把它显露出来，本来是埋在云里面，所以我们看到一堆恒星其实在这边形成。这章他就讲得更快，因为这不是这个演讲的主题，就讲到说，从一团云形成了一堆恒星，刚刚诞生的，有的恒星小，有的恒星大。刚才讲了，一团云收缩下去，中间做了恒星，事实上旁边那个还是一个扁盘的形状，一团小的气体是扁的形状，就跟我们银河系转得快，吹下去是一个扁的形状是一样的意思，对吧？那等一下才会讲行星的事情。不过中间的那个恒星呢，像太阳的稍微大一点的或更大的，它们在活着的时候，什么叫活着？在中间在行氢的核子反应，让它发光。我们说这个型啊，就是正在中年，在中壮年。有的恒星很暗，有的大质量的恒星就很亮。等它氢气用完了，它就演化掉了。我们太阳之后会变成一个红的巨星，比较比我们太阳大的，原来就是大的恒星呢，就会变成一个红的超巨星。它们的活着的时候，光耀的程度不一样，死的死法也不太一样。我们这种恒星慢慢把气体吹出来，造成一个行星状星云，气体散了以后，中间有一个白矮星，慢慢的去了这个黑矮星。大的恒星呢，它死亡的时候呢，就会用爆发的方式，而不是用慢慢吹散的方式，所以就变成一个超新星。虽然叫新星啊，其实它已经是星球演化末期的事情。那一样，云霄雾散了以后呢，就是它剩下的实体，就会要看它的质量，中间有可能变成一个中子星，或变成一个黑洞。这是很快的讲完恒星一辈子，从生、老、病、死，当然有很多专有名词了。星星跟人一样，有一定的循环。我们太阳这种恒星活这一辈子大概100亿年，这种很大的恒星活一辈子大概就是1亿年，几千万年甚至于非常短的时间就活完爆炸死。
If we follow the location of these different stars in a space described by temperature and by brightness or luminosity, we end up with something called a Hertzsprung-Russell diagram, which was already developed more than 100 years ago when people tried to understand the physics of stars. So along this axis here, we have temperature, higher temperature over here, lower temperature indicated by red over here. And on this axis we have brightness or luminosity. Very luminous objects are located up here, very faint objects are located up here. That time period during which stars are burning hydrogen in their cores is the main sequence phase that I already mentioned. Main sequence it is called because it really basically means that these stars are found along this sequence, this diagonal sequence, in such a Hertzsprung-Russell diagram. The most massive stars up here, the least massive stars, the most luminous stars and coolest stars down here. The lifetime now depends strongly on the mass of the stars. Stars up here have very short lifetimes of, well, a few million or 10 million years. Over here, we are already in the 100 million year regime. Here, we are in the billion year regime. Over here, we're approaching the position also of our sun. We are in the regime of 10 billion years or a little longer. And finally here, for the very low mass stars, which evolve extremely slowly, we are in a regime where they will never leave the main sequence within the current lifetime of the universe. They evolve much too slowly. They need even longer lifetimes for that. So overall, the lifetime of stars strongly depends on their overall mass. And that is also indicated here again for the main sequence with different masses expressed in the mass of the sun. The sun has a mass of approximately 2 times 10 to the 33 kilograms, very, very massive. And therefore, it's convenient to just use that as a unit of measure. And also the lifetimes are indicated here in units of years, 10 to the 6 years, 10 to the 8 years, 10 to the 10 years, you already see how that increases as we go to lower masses. Going just one slide back again. Other evolutionary stages that are reached later when the stars expand, later phases becoming red giants or red supergiants during other nuclear burning phases, are indicated here. For instance, this is the locus of low mass stars once they reach the red giant phase. Our sun would end up here once it has exhausted its hydrogen in its core. More massive stars become supergiants in this case and then evolve into supernovae. These stars here typically evolve into white dwarfs, then are very faint and have their locations down here. In this regime, they no longer have nuclear burning, they just cool out, essentially. So that is the overall picture of stellar evolution. With respect to nuclear fusion in stars, we do need relatively high temperatures to ignite nuclear fusion. Because to start with, we have, for instance, protons, which are positively charged, or other nucleons which are positively charged. That means they do not want to stick together. They repel each other because of their positive charge. So we need high temperatures in order to allow these nuclei to actually overcome this barrier that otherwise would prevent them from fusion. That means we need fairly high temperatures. In the case of nuclear fusion, temperatures of 10 to the 6, 10 to the 7 kelvins for hydrogen. For heavier elements, we need even higher temperatures than that. And that can only be achieved then in sufficiently massive stars. Stars overall always have an equilibrium, if they are stable, between their internal gravity, that acts inwardly, tries to compress these stars, and the pressure, in this case the radiation pressure, that comes from nuclear fusion processes that tries to enlarge the radii of stars. As long as these two forces are in equilibrium, basically we have stable stars, stars that do not change their appearance. There are certain evolutionary phases in which either gravity becomes dominant or radiation pressure becomes dominant, blowing up the stars, or leading actually to a contraction of the cores, increase of temperature, and possibly the ignition of subsequent nuclear fusion processes.
恒星是宇宙中间发光的基本单元啊，从研究这些刚才讲研究星系啊，都是靠发光的东西。恒星是一个很基本的事情。好在我们对恒星知道蛮多的。这张在高中里面的地科你们会学到所谓的赫罗图啊，两位科学家整理出来，它是整理这样是这个意思。这是恒星的表面的温度，热跟冷，这是恒星总共会发光的能力。所以比较亮的星，比较暗的星，就发现把这些星星啊，天上的星星啊，全部画在这张图上。不是它看起来多亮，而它实际上会发多少光线。如果把这个画上去，我就发现多半的星星都落在这个上面，所以这叫 main sequence， 叫主序。也就是说，恒星主要都待在这个阶段，好像人已经成长了以后，他的身高体重就是差不多这样，身高跟体重会有关系啊。所以为什么这条线很合理呢？单位面积很会发光，也就是很热，它呢发光就很强。表面比较冷呢，它发光能力就弱，所以这是一个正常的恒星，对吧？什么叫不正常呢？就是当它的核子反应啊，当它发光的机制啊消失的时候 ，next slide please。the next one。这个一个恒星像我们太阳，它中间一定要达到平衡。我们人也是活得要平衡，什么跟什么平衡呢？它的万有引力永远向内的力量，要跟它的向外的力量平衡。恒星如果有核反应，它产生的燃料、产生的能量，就可以让这些气体运动很快，彼此推开，就达到了一个平衡。大的恒星、中的恒星、小的恒星都平衡，所以它就处在一个主序带上面，很正常的现象。那可是刚才那个Grebel教授讲到说，恒星怎么行核反应呢？原子核跟原子核都带正电，你要让它融合啊，产生核反应啊，很困难的，因为它们彼此之间的排斥的这个正电力很强，所以一定要在高温的情况之下，才让原子核有机会靠得比较近。近了以后呢，就另外一种力量， 强作用力原子核的力量是吸引的力量，才让它从简单的原子核变成复杂的原子，就融合产生了核反应。所以核心只要是正常活着的，它就产生核反应，就平衡，就在九序上。一旦用完了它的氢，它就要产生变化，没有氢它就没有抗拒的力量，它就缩下去。可是，一缩下去，温度就上升，上升就可以让更多带正电的融合在一起，就是氦的原子，那就进行下一批的核子反应。核心的演化就是一连串的核子反应。
Just to show one example of such a stellar evolution as a function of time, here's an example for a star of the mass of the Sun. So if you wish, it demonstrates the projected evolution of our own Sun. Along this axis again, in the Church-von-Russell diagram, we have temperature increasing in this direction, highest temperatures over here, lowest temperatures over here, and here we have luminosities. After the Sun formed and started to ignite hydrogen in its core, it moved towards the so-called main sequence. This is where it is located now, burning hydrogen in its core. It can continue to burn hydrogen in its core for many more billions of years. It has already been on the main sequence for 4.5 to 4.6 billion years. Once hydrogen is exhausted, it will actually evolve further. First, the core no longer has support because the radiation pressure of the nuclear burning processes is missing. The star becomes cooler. It moves towards these regimes here in the overall Hertzsprung-Russell diagram. Hydrogen burning can continue in a shell around the core. In the core itself, there's no longer enough hydrogen, but in the surroundings there is. And the shells, the outer regions of the Sun will expand, making the Sun more luminous. That's why it moves up here. At some point then, the temperatures in this contracting core are actually high enough for helium burning to start. So instead of burning hydrogen to helium, we are now burning helium to heavier elements. And that continues in this evolution. The Sun moves back towards a location similar to its previous one, but now burning helium in its core. At some point, that helium gets exhausted. The Sun can no longer continue, and it's not going to reach sufficiently high temperatures to experience subsequent burning processes of, for instance, carbon or oxygen, which are created in this helium burning. That means the core star, basically the core shrinks again, the outer regions get ejected, forming a so-called planetary nebula. Planetary nebula has nothing to do with planets, it just looks like a planet as an extended source in telescopes. A few hundred years ago, that's why people called these objects planetary nebulae. And ultimately, also, these ejected regions around the star, these ejected atmospheric layers, will no longer be sufficiently luminous to be visible, and what remains is just the core, the compact core that no longer has any fusion, and that's the white dwarf. The white dwarfs continue to cool down, ending up here in this lower portion of the diagram with a very small radius. That would be the typical evolution of a low-mass star like our Sun.
好，这张图当然就是刚才的那张投影片是比较有学问一点的，就是把这个太阳的演化呢放在赫罗图上，还是一样，温度向左增加，亮度光度向上增加，所以太阳在这边一直核心在燃烧氢，已经燃烧了45亿年了，估计它还可以再燃烧50-60亿年。等它核心用完了氢以后呢，它核心缩下去。变热了，变热后就把外围给往外推，所以外围就膨胀，一膨胀它就变冷。可是因为它膨胀，它就变得比较大，比较亮，亮度增加，但是温度降低，它就变成一个红巨星。然后呢，可是核心缩下去了以后呢，核心够热了，就点燃了氦，你在这边点燃了氦，所以这边它在燃烧氦，氦又用完了，又缩下去，又把它的壳层又往外推。太阳就变成一个红的超巨星，所以在这边太阳在这边很不稳定，一下缩一下涨，一下缩一下涨，到最后那一次把外层那个 shell 组成的这个eject把它推出去，核心呢缩下去变成一个白矮星，外层的大气层没有用掉的氢 就抛出去，叫行星状星云。刚才那个 Grebel 教授解释，行星状星云跟行星是没有关系的，只不过早年在望远镜里面看起来就是一团云，好像行星的样子，所以把它叫做行星状星云。它事实上跟行星无关，它事实上是太阳这种星球晚年吐出来的一口气大气层喷出来。那气慢慢消散掉了，中间那个白矮星呢，一下子就冷却了。对不起，刚开始白矮星很热，因为白矮星是原来的核心嘛，是来自核子反应的那个反应炉就出现的时候就变得非常非常热。可是呢，因为它没有核子燃料，所以它唯一的一条路就是冷却，所以它就一直不断的冷却，随着时间下降就越来越暗，越来越暗。这张图总结了从现在开始，过去的46亿年一直在这边，跟未来的大概70、80亿年太阳的演化的路径。
So what is the end product of the evolution of the star, the mass of the sun, similarly low mass stars, is basically the ejection of nitrogen, helium, but also heavier elements such as carbon, nitrogen, oxygen that originated in subsequent nuclear burning processes of the sun. Here you see a schematic illustration of hydrogen burning, where individual protons fusion form deuterium, tritium, and ultimately helium. Over here you see the subsequent burning processes that happen on the red giant branch when helium burning is ignited. Helium atoms then can fusion to form beryllium, and heavier elements such as carbon, for instance, form nitrogen and oxygen. And that is what gets ejected during the planetary nebula phase, already polluting the surrounding gas with heavier elements. And importantly, these kinds of elements, carbon, nitrogen, and oxygen, are major elements for life as we know it. We consist to a large proportion out of carbon, nitrogen, and oxygen, of course also nitrogen, which then combines with oxygen to make water. Basically all living beings that we know of have a large proportion of carbon in them. Carbon is one of the important elements for life. If instead we look at more massive stars, those stars that ultimately will become supernovae and neutron stars or black holes, we can also have the production of heavier elements. For instance, these stars reach sufficiently high temperatures to fusion carbon to, for instance, silicon, or oxygen can fusion to form sulfur or silicon itself. Fusion here produced earlier in earlier burning phases. Once enough silicon is there and the temperatures are high enough, silicon can fusion to form iron. Iron is the heaviest element that can be produced through nuclear fusion processes in stars. Subsequent element production happens usually in the end phases of supernovae through the capture not necessarily of these heavy nuclei or protons, but through neutron capture. And that allows us then to form elements even as heavy as uranium, and a number of unstable and stable elements that are fairly heavy, which we find as trace elements also on Earth. In these more massive stars, we typically then find multiple layers of nuclear burning phases with increasing temperature towards the inner regions. The outer regions may actually have hydrogen fusion. As we go more inwards, we have helium fusion, carbon fusion, oxygen fusion, neon fusion, magnesium, silicon, until we reach this iron core. Once we have reached the state of an iron core, which then can no longer continue to experience fusion because heavier elements require the addition of energy. They do not release energy in fusion processes. They're actually created through fission, as it's called. Then we have the state at which this object will become unstable. It's no longer supported by radiation pressure in its inner region. The core collapses. We have the stage of a supernova in which these final stages, a number of heavier elements can be created. The supernova will release elements not only like carbon, nitrogen, and oxygen, but also magnesium, silicon, iron, and a large number of additional elements, which again are essential for the formation of planets and subsequently for the formation of life.
超级复杂那我长话短说，就是大质量的恒星，它温度高，所以它可以融合 不同的元素啊，带正电量比较高的，它也可以让它融合，所以有可能会把碳，它可以燃烧碳变成气啊，然后变成这样的力量啊，变成硫等等等等。那最后啊，就最终产物啊，靠融合，就是简单的原子核变成复杂原子核，只能到铁。这个我刚刚坐在那边想到一个例子，就是我们平常你撒米啊，你把米倒到米缸里面，你倒你去抖一抖，你抖一抖，它会怎么样？它会沉下去，所以你米越倒越多，它越重的时候，它会去塞空间，对不对？就这个意思。所以原子核啊是这样子，我把一个原子核跟另外一个原子核靠强作用力结合，它变成新的原子核，它把自己拉得更紧，拉得更紧，所以它更紧的放出来的力量，就是原子核的束缚的，原来把它抓住的能量，那就是原子核的核能。可是这个紧的程度啊，到铁。比铁更重的东西，我那个米缸到后来，你再加啊，它就满出来，它不会再缩下去。所以铁之后的原子核，你再加原子核进去，它不会缩下去，它已经达到最低的状态了。你再加原子核，它会膨胀。所以靠核融合来取能量，直到铁。所以恒星就靠核子核，之前讲的那个 Big Bang 讲的那个 nuclear physics， 核融合是产生的一种。后来的宇宙全部靠恒星在做这个东西，所以核心的这种大质量的核心啊，中间温度最高，所以它烧最重的元素，然后慢慢核融合越来越像洋葱一样一层一层。等到它，就为什么它这么会发光，它这么亮，因为它有很重的原子核在进行核反应。可是等它死亡的时候啊，也是一样，没有核燃料了，爆发的方式，超新星爆发。几个月之内亮得不得了，可是它的遗骸啊，它的剩下来的尸体呢，就留在这边。那这遗骸炸掉以后，很多产生的这些重元素啊，就又回归了星际物质，做了下一代的恒星，包括了做地球以及地球上的我们身上的所有这些复杂的元素，铁啊、钙啊、锰啊、什么锡啊，那全部都是恒星做的，我们都是恒星做出来的，剩下的都是。
What you see up here is a so-called supernova remnant, consisting of the material ejected in such a supernova. So we said essentially all of the outer regions of the star get ejected. This region here, this material is highly enriched in these heavier elements. This material can merge with the surrounding or get diluted into the surrounding gas, into the surrounding so-called interstellar medium, can be used for subsequent star formation. Meaning that stars that form later on will be increasingly enriched in these heavier elements. Of course, they still mainly consist of helium and hydrogen, but still they also have an increasing composition in these heavier elements. And that is important for stars like the Sun. It's also important for the material around stars that contributes to the star formation. This material in these accretion disks of protostars can be used for the subsequent formation of planets. We look at the overall element abundance distribution as it is observed in the nearby universe. We still find, and this is a logarithmic scale of the relative abundance, we still find that hydrogen is by far the most common element, still the most numerously occurring element, followed by helium. But then subsequent elements that get generated in stars, and essentially everything over here in this part of the diagram, heavier than helium and beryllium and lithium, are elements that get generated in stars. All of these are elements generated through stellar nucleosynthesis or explosive nucleosynthesis in supernova explosions. You can see how these abundances rapidly drop as we go to heavier elements, which then become increasingly rare. The relative abundances of individual elements depend on the specific nuclear burning processes in which they can be created. So with that, we are basically ready to have enough heavy elements to start to form planets. And that leads me to the last chapter, planetary systems. The first planets were discovered in the early 1990s. In fact, the first planets around a normal star were discovered in 1995. So it has been a relatively short time overall that we have known of the existence of extrasolar had been hypothesized already a long time ago. Just the absolute proof happened later on. There are a number of different techniques that can be used for the detection of planets. For instance, one can use the mutual gravitational pull between the planet and the star around which it orbits to detect this in spectra by looking at the motion, the apparent motion because of this gravitational pull. Other methods rely on transits where planets basically obscure a small portion of the star while they pass in front of the star, seen from us. These are so-called planetary transits that can be observed through changing light curves. It's a very small effect, but still something observable. And there are a number of additional techniques that can be used. One technique that one can use only in a few rare cases where one gets extremely lucky is actually direct imaging of planets. And one such example of direct imaging is visible over here. This is taken with a technique in which the starlight of the central star gets blocked out. The central star is not really visible, it's just marked by this little white spot that you see here. This is a star that is surrounded by a very extended dust disk, dust and debris. So it's still a star that is a fairly young object. This star here, overall Fomalhaut, is a fairly massive star. It's a so-called A star, meaning that it's more massive than our own sun. It's at a distance from us of only 25 light years. The star, or the surroundings of the star, were observed over several years. And people noticed that in this extended dust disk that you see here, there are a few objects that are relatively compact and that change position as a function of time. Here are two observational points obtained in 2004 and 2006. This little object is believed to be a planet orbiting around the central star. Within this short period of time, one can actually already see a little bit of the motion around the central star. Of course, through subsequent observations, this has been confirmed and one can get some idea of how fast it moves around Fomalhaut. However, that is an exception. In most cases, we cannot see the planets directly. In most cases, they are too faint and too distant, and we can just infer their presence indirectly through other types of detection techniques. Now, the question is, how do planets form? We believe that planets form in the extended accretion disks of material that also contributes to the formation of the protostar in the center of such an accretion disk. So we are back now at the early stages of star formation. In the central regions of an accretion disk, we have the very high density where the central protostar is forming. The star is surrounded by an extended gas and dust disk. And it's believed that in this gas and dust disk, instabilities can form, small dust grains will be present. These dust grains can actually collide with other dust grains, stick together, and form subsequently bigger and bigger objects. Individual steps of this process are shown here. We have initially tiny little dust grains of the size of micrometers, so even less than what we can observe with our eyes. These individual dust grains can stick together, they can coagulate and form bigger dust grains. It is believed that this process continues on time scales of several thousands of years, that is this phase over here, and that they grow to bigger and bigger units. It's a slow process, and of course, these units, or the growth that needs to be overcome to form a planet, covers many orders of magnitude. Ultimately, a planet has sizes of, well, a few times 10 to the 8 meters. The dust grains initially have sizes of 10 to the minus 6 meters. You see it's 14 orders of magnitude across which growth has to occur. Starting out with these tiny little dust grains, we move on to increasingly larger and larger bodies, which finally are large enough that their individual gravity is sufficient to keep them together and to attract additional material on their surroundings. It's like a large-scale structure, we now have growth through gravity, even on very small scales, up to the size of meters, of kilometers, of tens of kilometers. Once we are in the regime of several tens of kilometers or hundreds of thousands of kilometers, these objects are big enough to begin to attract also surrounding gas. They begin to form gaseous atmospheres around them. And that is basically the late phase of planetary growth. It can either lead to the formation of a gas giant, which then has a rocky core, or it can lead to the formation of more terrestrial planets, which may or may not have an actual atmosphere. This growth also depends on the proximity to the central star. The central star, the central protostar, of course, begins to get hotter and hotter, and its radiation actually drives away quite a bit of the surrounding gas, leaving mainly heavier elements in close proximity to the central star. Lighter elements can survive at larger distances, and that means that it's a little easier to form rocky planets closer in. Gaseous planets can form more easily at larger distances from the second star.
很快的讲一下这个系外行星呢，是现在很热门的一个课题了，因为这10年左右才大量的发现这些太阳系以外的行星。那我们自己是住在行星上嘛，我们对行星当然非常感兴趣。刚刚讲的那个恒星啊，在这个一大堆云里面，它收缩旋转变成一个扁盘状，中间做了一个恒星。刚刚讲恒星的演化，现在讲行星。在这个盘状结构里面呢，跟刚才的宇宙大尺度结构很像，是由小而大这样长大的过程。原来的尘埃很小，一个 micron 比我们那个平常汽车喷出来的那个烟还要再小10倍，眼睛看不到。这种小的尘埃，慢慢聚集在一起，粘在一起，长在一起，变大了以后，差不多像台中市这么大的这种小行星等级的呢。它就不再靠粘的，它靠万有引力，所以它在走在路上，它就把这小东西吸过来，它就慢慢长大。所以由小慢慢长大，变成盘子越来越不均匀，到最后长得非常大了以后呢，它就可以吸周围的气体。这种就像我们地球这种长大变成岩石状的行星，如果再花时间再长下去，就跟我们讲时间了，100万千万年的时间呢，它就可以吸到大量的气体，一旦能吸大量的气体，因为一流仪器里面都气体居多了，它就可以长得非常大。所以我们的木星啊、土星啊、天王星、海王星，就属于这个等级的，它是属于离太不远，所以它的气体呢可以吸得住。我们地球离太阳太近，气体一吸跑得很快就跑掉了，所以我们地球就吸不住气体，我们就只有很薄的一层大气。
There are many questions still open in planet formation, especially the growth across such a huge range of different sizes is quite uncertain in its details, how that really happens on which time scales exactly. It is believed that overall the time scales for planets to grow and evolve are of the order of a few 100 million years, with different speeds for individual processes here. However, I don't know if you can read the small print, but it says in many cases quite uncertain. Many of this is still not yet very well understood in detail. We are working on improving these kinds of models. With respect to which planets can form where, the current theory is that because of the radiation of this protostar that forms here, the inner regions, we will mainly have heavier elements that remain, that can accrete, that can lead to the formation of rocky objects that increase in size, that stick together through their gravity, and that lead to the formation of terrestrial planets like our Earth, like Mercury, like Venus, like Mars. At larger distances, where we have lower temperatures, also lighter elements can remain. They're not as strongly affected by the radiation of this central star that is gradually forming. Here, we can actually have surviving ices and cooler and lighter material, such as, well, for instance, helium or other light elements. The assumption is then that if we have the formation of rocky material also here, this rocky material is then able to accrete gas from the surrounding nebula, leading to the formation of very large gaseous envelopes of, for instance, hydrogen, helium, or other light elements, basically the formation of gas giants, such as Jupiter or Saturn. That at least is the general idea. So first we have a rocky core of several Earth masses actually, very massive objects, and then these cores accrete stars until we have massive gas giants that survive here at these larger distances. Now, with respect to observations, one interesting observation that people made early on was that they found gas giants at distances very different from where we find them in the solar system. In the solar system, we find them far beyond the orbit of Earth. They are at fairly large distances from the Sun. Observationally, the early observations of exoplanets led to the discovery of very massive gas giants very close to their central stars. It was a completely unexpected location for gas giants. A theory to explain that suggests that these gas giants may have formed further out, and so various processes of instability, such as encounters between many of these forming objects, were brought further inwards. That's one of the theories to explain that. Another question is, of course, whether our solar system is generally representative for more distant systems. There is a certain detection bias because our detection methods allow us to detect massive